We say two events A and B are independent if the probability that A and B occur is equal to the probability of A times the probability of B. So we're going to start with an example, which is the classic coin flip example. And you always said that the flips of the coin are independent. And here's another way to look at that. So let's say we flip a fair-sided coin twice, and A is the event that the first flip is a head, B is the event that the second flip is a head, and C is the event that the second flip is a tail. So the sample space of all possible outcomes of two flips is heads heads, heads tails, tails heads, or tails tails. And each point would have probability 1/4 because each outcome is going to be equally likely. We can write the events as subsets of the sample space. So A, the event that the first flip is a heads, would be the outcome of getting heads heads or the outcome of getting heads tails. B, the event that the second flip is a heads, is either the outcome of heads heads or tails heads. And C, the event that the second flip is a tail, is either the outcome that we get heads tails or tails tails. So let's compute the probability of these events. The probability of A we can compute by using the fact that A is the union of heads heads and heads tails, which are two separate points, and since they're single point sets, their intersection is empty. And therefore the probability of A, which is the probability of heads heads or heads tails, is the probability of heads heads plus the probability of heads tails, which is 1/4 plus 1/4, which equals 1/2. And by basically the same kind of computation, the probability of B is 1/2 and the probability of C is 1/2. So if we take the product of any two of these, for example, the probability of A times the probability of B, we get 1/2 times 1/2, which is 1/4. Also, the probability of A intersect B is the probability of a heads 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 tails intersect a heads heads tails heads, which is the probability of heads heads, which is 1/4. So the probability of A times the probability of B does equal the probability of A intersect the probability of B. And this means that A and B are independent events. Similarly, you can show that A and C are independent events. So the product of their probabilities is 1/4, and if you intersect heads 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 tails with heads tails tails tails, you get only heads tails to get the first flip to be a heads and the second flip to be a tails, which has probability 1/4. So A and C are also independent events. But what about B and C? So the probability of B times the probability of C is also 1/4, but the probability of B and C is the probability of getting heads heads or tails heads, so a heads on the second flip, intersected with heads tails or tails tails, which is a tails on the second flip. And it's impossible to get both a heads and a tails on the second flip, so this is the empty set. There's no case in which we would get both the heads and the tails on the second flip, and the empty set has probability 0. So B and C are not independent events. Independent events are easy to work with usually, and you're often told that the two events are independent. You don't figure out whether they're independent, like we just did above. But there's also a lot of misconceptions about independent events. So I want to give a visualization here. So in this case, the sample space is going to be the box, that's omega, and A takes up 1/3 of the box. So we'd say that A has probability 1/3, and B has probability 1/2. So notice that A and B don't overlap completely with each other. A is not contained inside of B, and also they're not completely disjoint. So it's not like we have A over here and B over here or something. And in fact, the way that they overlap is A takes up 1/3 of the whole space, and A takes up 1/3 of B. And on the other hand, B takes up half of the space, so we could think of the probability of B as a half, but also B takes up half of A. So we're going to look at each in turn. A is 1/3 of the entire space, and if we look at B, which is this set here, then A takes up 1/3 of that set. And similarly, B is half of the entire space omega, and if we look at the set A, which is here, this red box, B takes up half of A. And since B takes up the same amount of A as it takes of the whole space, and A takes up the same amount of B as it takes of the whole space, that means that A and B are independent. If A and B are independent, then the probability of A given B is just the probability of A. And since order doesn't really matter here, the probability of B given A is also the probability of B, because if A is independent of B, B is independent of A. So that's where order doesn't matter. I should have been clear on that. So conditioning order does matter, but independence, it does not matter. You can show this by the definition also. So the probability of A given B is the probability of A intersect B divided by the probability of B. Then, using the definition of independence, the probability of A intersect B is the probability of A times the probability of B. And that allows you to cancel the two probabilities of B, which gives you the probability of A. So if events are independent of one another, that is, they don't affect the outcomes of each other, the probability of one event given the other one is just the probability of that event itself. It doesn't change. And that's where some of that intuition comes in from the picture that I'm wanting you to develop. So if the probability of A is a third, then we're given B. Well, A takes up a third of omega, but A also takes up a third of B. So it doesn't change the probability that A occurs. It's still 1/3. If A and B are independent, then so are A and B complement. And you can prove this. So if A and B are independent, we can write A as A intersect B unit A intersect B complement. That is, A is everything that's in A and B and everything in A that's not in B. And since these two sets are disjoint, since there's nothing that's in B and B complement, we have the probability of A is the probability of A intersect B plus the probability of A intersect B complement. Now we can compute the probability of A intersect B is the probability of A minus the probability of A intersect B, the probability of A intersect B complement. And that's just by subtracting this one to the other side. Then the probability of A minus the probability of A intersect B is equal to the probability of A minus the probability of A times the probability of B. And that's just by independence of A and B. Since A and B are independent, this is the product of the probabilities. Then we can factor out the probability of A to the front. So this is the probability of A times 1 minus the probability of B. And the 1 minus the probability of B is the probability of B complement. So P of A intersect B is P of A times P of B, which by definition means A and B complement are independent. You could also do this with A complement and B, or A complement and B complement. So when A and B are independent, so are A and B complement and B, A complement and B complement, and so on. And finally, I squeezed in a definition at the end, but it's an important definition. So if we have a collection of events, AI, over some index set I, we say that that collection is a set of independent events if, for every finite subset J contained in I, the probability of the intersection over all the sets in J in the index set is the product of the probabilities of the sets. So that works for every finite subset J of I.